Hadoop ecosystem is in large parts also the basis for subsequent developments such as Apache Spark. And Hadoop was basically the first cluster computing framework which has gained widespread attendance. So let's look into this. First, a summary from the last lecture. So we talked about virtualization. We talked about Java virtualization, which is often used by cloud providers, full virtualization, partitioning, hardware emulation, application virtualization, and hardware virtualization, and finally containerization. We also had a look at Amazon Web Services, which is basically a collection of cloud services, and the services which are the highest relevance if you are looking at cluster computing are the Elastic Block Store and the Simple Storage Service for storage, then the Elastic Computing Cloud or EC2 for virtual machines, and the Elastic MapReduce service for cluster computing on top of EC2 instances. And finally, there's Lambda, which is a serverless computing service. But of course, there are many more services for authentication, for any kind of databases, etc. So we also discussed this EMR workflow. So the takeaway message here is that basically, if you want to do something with EMR, then make sure you are sure that it works. So before you actually scale up the workflow, so first try it with a small subsample, and then if it works, scale up. And don't run the job with high workload immediately, otherwise it might get very expensive. And of course, might be a little trivial, but never forget to terminate the cluster on the poor person. Okay, and then we just a little the topic of serverless computing. Of course, it's very convenient. You don't need to do any server management, and you have a linear increase of the cost along with resource usage. So it's really scalable with basically no effort on the user side. And it's also very fast. You can easily deploy updates. But of course, the downside is that it's a vendor lock-in, a very hard vendor lock-in. It's very hard to actually move the service away from Lambda, for example. It's also difficult to debug your applications, and it may also be susceptible to vulnerabilities. And there's, of course, a premium involved for this convenience. Okay, so to sum this up, AWS has two services which enable the managed controlled usage of a large number of resources, which is EMR and Lambda. And the services are basically always controlled by a REST interface, and everything else, like the web console, the command line tools, also the Java APIs, are just a front end to the REST interface. So behind the scenes, they're all using the REST interface. The costs are roughly proportional to resource usage. And if you want to store large amounts of data, always use the S3 servers. This is the cheapest by far. Okay, so let's have a look at Hadoop. What is Hadoop? Hadoop was released in April 2006. The first release was in April 2006. So it feels a little bit like the Stone Age from computer science. It's developing very fast. Still, it's of high relevance for today. Also, it's still being actively developed until today. Some modules which Hadoop consists of. These are the Hadoop Common libraries, which are the basis for Spark, for example. Hadoop Yarn, this is a resource manager. It has been introduced in 2012. Hadoop MapReduce. I will talk a lot about MapReduce later. And there are also some other parts which in a more wider sense, belong to the Hadoop ecosystem. So they're not directly part of Hadoop, but they are part of the ecosystem. So these are surrounding tools which you may or may not need to do something with Hadoop. For example, Apache Hive, which is a wrapper for SQL-style queries on Hadoop. And then HBase is a NoSQL database. So you can either have SQL-style queries or NoSQL database. Then there is Apache Zookeeper, which is used for the coordination of cloud applications. This analogy of having different animals and someone who keeps them all together. Apache Impala, that's used for massive parallel SQL queries on Hadoop. I guess an Impala is some kind of animal, I don't know, unicorn or something. Anyway, and Apache Uzi, which is a workflow scheduler for Hadoop. Okay, so at the very core of Hadoop, there is the MapReduce framework. What's MapReduce basically? MapReduce is a program model for the distributed parallel processing of large data sets on a cluster. And its basic principle is that there are map functions, which are basically just projections, and we have the use functions, which are used for data aggregation. So the basic workflow is, for example, you can have this input data, which just consists of three numbers. So you have a sequence or a set of three numbers. Basically, the abstraction is the set, so it's not a defined order of processing, because it's yes, that's the process. We process in parallel, so it's a set. And then the set is mapped to the map function. This is the projection, and the function could be something as simple as projected to the square of the number. Like in this example. So now we have a different set, which has been created out of the projection of the mapping function. And now, we have projected values, but they still separate. And usually, if you are employing a class style, you need to somewhat aggregate and unify your results. So usually, you want to somehow create a combined result out of several individual results. And that's what these reduce functions are for. So basically, a reduce function defines how two values of the set are combined to create a single new element. And for example, this could be like this function, which basically just says that any two values out of the source set are projected onto the addition of these two values on the destination set. So it's also just a function, but a function which projects a tuple of two onto a single value. And at the end, you have a result of the data aggregation, which is just a single value. So all the set becomes aggregated to a single value. Of course, it doesn't need to be this way, so we have different types of aggregations. But the basic idea is always that you have a mapping step and a reduce step. That's why it's called MapReduce in the first place. So the principle is the application of an identical mathematical operation on all elements of a set. It's important that you are doing all the same with each value, because otherwise you won't be able to scale it up in parallel. So mathematically, it's just a projection with a fixed definition range and also a fixed value range. And the map operation specifies the projection, but it does not specify the method of parallelization. So this is very important, because it's some kind of abstraction. It doesn't just tell you what you want to do, it doesn't tell you how you can actually do it. So that's up to the framework. That's also a big difference to low-level parallelization frameworks, because here we can just say we want somehow this mapping to be performed, but the way it's parallelized is up to the framework. Of course, you can configure it, but still the framework finally decides how it is parallelized. yeah, there are also purely sequential implementations available, of course. For example, from the Java Streams API, there's a non-parallel version of the Java Streams API that's basically just the simplest one, so we probably already have worked with this. And this, yeah, as I said, it's non-parallel, so it's purely sequential. So basically, yeah, you can do the same sequentially using the same interfaces. And in mapping use, these map operations are also used for filtering and sorting data. I mean, it's obviously you can just define a filter function using a mapping function, also sorting data. So you probably already know this, but just to repeat it, maybe it's not so present anymore. So this is a bidirectional mapping, the most simplest form of mapping. And yeah, so you have source set and destination set, and each element of the source set has exactly one counterpart in the destination set. It's all pretty simple. We have, so every projection has at most one target and also at least one target, so exactly one target. But there may also be a surjective mapping. So in this case, yeah, we have several elements of the source set may be projected onto the same in the destination set, so it's not injective anymore. But it's surjective, so surjective means that every element in the target set has a counterpart. So A, B, C, D, they all have like a source element. So the mapping here is surjective, but it's not injective, so that's why it's not bijective. Injective mapping is something like this. So yeah, we have there may be elements in the destination set which don't have a counterpart, but all elements have exactly one counterpart in the source set, so not more than one. So then it's called injective mapping. But of course you can have mapping which is neither surjective nor injective, and also of course not bijective, like this. So in this case, if the mapping is not injective, then you don't have a well-defined reverse mapping, right? So if it's injective, then of course you can always just reverse back and forth infinite times without losing any data. If it's not injective, this won't work because you have ambiguity here, right? So if you want to go back, you don't know should I project the D onto the 4 or the 5. So that's like a work. So this kind of mapping also exists, of course. And yeah, of course, it's the most complex kind of mapping. Yeah, then there is an operation called flatMap, which is basically just flattening sets. So if you have a set of sets like this, then you apply a flatMap operation, which all the bubbles will be like resolved. So you finally end up with a single set which contains all elements of the individual sets. So that's the idea of flat mapping, just creating one single flat map out of lots of flat set of sets, or set of sets, yeah. Lots of sets of sets, yeah. Okay, so what's the reduce operation about? It defines operations which aggregate the results of parallel calculations, yeah, like in this example. So a simple reduce definition just creates the result of the addition of two elements. For example, if you would want to count all words of a text file, you could have a level of parallelization on the level of individual lines of the text file. So every line of the file could be processed in parallel, so you want to have individual worker instances working on each line of the file. Then the map function would project a line of the number of words which are contained in the line. And the reduce function specifies that the overall result is given by the sum of all word counts of all lines, right? So just adding up all word counts of all lines. So we have parallelism, that is present on the line level. That means that every line of text could be processed as a separate job on its own. You have always to be aware about the level of parallelization you need, right? Because it could, it really depends on the problem, but you need to be aware that, of course, you cannot go more fine-grained in the level you have defined. So, it might be too coarse in some situations if you really work. So always think about what should be the atom, so the atomic operation, which cannot be divided anymore, and what should actually run on separate nodes. Like in this case, you should say, okay, once per line is fine. And also say like every 4 lines are directed to individual nodes, so maybe this is enough. It really depends on the problem. So the idea of MapReduce is a special form of the so-called split apply combine principle. Like in this nice visualization here. So first you have this kind of unstructured data, like all this Lego stuff, and then you have a breakdown of a data set into groups according to criteria which you define, of course, like this. In this case, you can say, okay, we are breaking them down based on the color. It could be something else like shape or whatever. Quality, you name it. So the criteria are up to you. And you could also then apply a function individually to each group. So the idea is that now I have separated all these separate sets by some well-defined criteria. I can now apply a function separately to each of these groups. And finally, I aggregate them into a single program result, like this update. So that's the basic idea of split, apply, combine. And how is it implemented in Hadoop? First, for the map operation, so every node applies the map function to local data by using a so-called wrapper, and then writes the result into a temporary storage. So this is important because it's what actually makes Hadoop slow compared to Spark, because it's always using this temporary storage. So it's not actually ignoring the RAM, it's always using the storage. And the master node ensures that redundant input data are only processed once, so we have, of course, some coordination involved. And then we have a shuffle step, so data are redistributed among the nodes, depending on the result of the map function, of course. So the results of the mappers then become the inputs of the reducers. So the reducers are used to actually reduce the result of the map function. Therefore, the results of the map function are sorted and partitioned so that they can be consumed by the reducer. Then the reducers create the actual reduction or unification of the results. So, of course, in order to actually process the results and do the reduction step, we first need to do the shuffling so that the data are actually there where they need to be processed. This is, of course, also the case in Spark. It's always, obviously, it's required that the data need to be on the exact very node where they are being processed, so, or the reduction to work. Okay, so basically these 3 steps. This would be like, pseudo code for Hadoop for this word counting problem. So we have this mapping function, and the mapping function would get a string, array, and the document, and then would look for every word in the block and add, every word would add a tuple of the word itself at the number 1 to the result here, because each word is just 1 or more, right? So we count the words, and then we return a hash map with the word as the key and the word count as the value. Then we have the reduction function, which basically takes a word, an iterator, And yeah, the framework actually moves the results by the key. Then it calls this function once per key. So yeah, like here, so we get the iterator and then we loop over the iterator. And the iterator provides all the results of the map function. I get next, so we always get the next element in the iterator. The iterator says more elements in the step. And now, yeah, we actually, in this case, we have implemented a reduce function as just the sum of everything. So we are pretty straightforward. So this is the definition of the reduce step here. And finally, we return the aggregated result, so we return the same words, but the sum of all individual numbers, which is of course more than, can of course be more than one. Yeah, there are some components which are customizable in the Hadoop MapReduce framework. First, the input reader. The input reader is responsible for dividing the input data into manageable parts of roughly 64 megabytes, which are then directed to a map function. So if you have very large input data, they are divided into small parts. And the data are read, for example, from a distributed file system, such as HDFS, I will come to this later, and they are transformed into key value pairs. So Hadoop is always working with key value pairs, not with individual numbers. It's always this sequence of key value pairs. So the map function obtains a set of key value pairs, and then applies the mapping function to every value, and thereby it creates a result pair of the arbitrary key, which is often the same, and a transformed value. And be aware that the cardinality of input and output data sets is not be identical. So yeah, you may have 1 to n or n to 1 transformations. So it doesn't need to be a bijective mapping. It can be any kind of mapping. But if you have something else, then bijective mapping you should be aware of the partitioning. There is a partitioning function which assigns the output of the map function to a reducer based on its key. Yeah, so it's depends of course on the key which is the responsible reducer. Because the data need to be directed to a reducer works on them. And yeah, its target function is to achieve a uniform distribution of the keys among all reducers. So the idea is that yeah, the reducers are somewhat work on get an equal workload or roughly equal workload. So we have a roughly even distribution, a uniform distribution of the keys among the reducers. Of course, this might not work perfectly all of the that's the optimization goal for the partitioner. And finally, we have a shuffle step. So data are moved from the creating node to the node which is scheduled to reduce them, of course, so otherwise you wouldn't be able to reduce them. So these are the customizable components of the MapReduce framework. We also have a compare function, which is basically just the definition of equality, because the input data are sorted as a preparation for the users, and of course, in order to sort data, you need to define which are equal and which are not equal, so what equality actually means. And then the reduce function itself is called once per key in the sorting order, and it iterates over all values which are assigned to this key. So, as I said, it's not necessarily a bijective mapping. So it may create a single output element, it may create multiple output elements, or it may also create no elements. This is also important. You may have just empty set as a result of the mapping. So the result of the reduce function. So like the empty set is also a possible output. And yeah, for example, in the word count application case, then we have input pairs which consist of the word and the count of the word, so the number of occurrences of the word on an individual node. So yeah, this may be more than one, of course, depending on how many occurrence of the word have been in a single line, as we said, so each line gets directed to a different node. But we have multiple input pairs, so in this case all the different lines of the text which have been mapped to the word and the number of occurrences of the word. But there's only one output pair, which is the word and the total count of the occurrence of the word. So yeah, basically it's just joining input pairs to a single output pair. As I said, Hadoop is always working on the value pairs and not on individual values. And finally, we have the output writer, which writes the results of the reduce function to persistent storage. But there are some constraints for the reduce function. So which are these? Mathematically, there are two conditions which must be met by the reduce function. The first one is the associativity. This is, you can't be aware of it. So it just means that if you have an operation which has the property that A and B are used and then C, it should yield the same result as first applying B and C and then A operation. So for all A, B, C, out of the evaluation of the map function, so it needs to be associative. And then you also have to have a neutral element E, so that basically applying E and this and any value is invariant, so that actually you get the same element. For example, for multiplication, the neutral element is obviously 1, so multiplying anything by 1 doesn't change the value. For addition, it's 0, like adding 0 doesn't change anything, right? For subtraction, it's also 0. So there must be a neutral element for all elements in also the value range. And the neutral element must, why does it have to exist? It must exist so that nodes which do not get any data do not affect the result, right? Because otherwise, if we had the joining of the empty set and another result, then the result could be changed by the operation. So to prevent this, we need to have a neutral element, which is basically it's a 0 or 1 element, whatever the operation is. This is equivalent to this algebraic structure called monoid. Which defines the set in the operation of neutral element. In this case, B is the value range of the map function. So the mathematical requirement is we have a monoid. And this value range, this operation, is this element. And just give you some additional context. So if there's also inverse element, we call this group, and there's also commutativity, we have actually the Billion group, and if you have the Billion groups K plus and K equals 0 and multiplication, and distributivity in K, you even have a field, so which specifies the field extents. So probably stuff you have heard of in mathematics, etc. Anyway, so let's keep in mind that we need associativity and neutral element for the reduce function. Be aware that not all possible binary functions satisfy both of these conditions, and some you might say it's trivial, but in some cases it's not. At least I think so. So, for example, the average, the average could be handy, but average is not associative. Like in this example, so if we have like 1, 2, 3, 4, so the average of first and the average of 1 and 2 and then of 3 would be 2.25, but if you do it the other way around, you get 1.75. So it really depends on the order of applying the average function to change the result. So it's not associative. And it's also, there's a neutral element. For example, the average of 0 and anything is not anything, but it's always the half of it. So there is an initial element for the average function. So it, for example, it wouldn't work for SI reduced function. What are the performance considerations for MapReduce? We need a balance between the cost for the CPU time and the data transfer. And since it's a property of Hadoop that it's always persistent data on intermediate storage, and this often means that we have a dominance of data transfer cost. So it's often bound by the data transfer cost rather than the CPU time. And the performance is basically dominated by the amount of data created by the methods. So if the intermediate results do fit into the working memory, to the RAM of a node, then don't use MapReduce. So it's always still more ineffective than Spark. So use Apache Spark instead. And I would like to add that if your results do not fit into the RAM, but you should also use Spark and think about how you could make them fit into the RAM. So basically, there are not so many applications I would see Hadoop relevant as of today, but still it's of the high historical importance because Spark uses the same interfaces to a large part and also the same ecosystem. But of course there are some applications where it might not play a big role, whether to use Spark or Hadoop. But also I think that the problem formulation is more difficult than Hadoop and Spark. I mean, this word code example is quite easy to understand. That's why you always get the word code example if you look for examples, but there are some other applications which can be very, very hard to actually map a problem onto the way of Hadoop. So the concept of Apache Spark is that if tasks are failing, they are simply rerun. So then any calculated results are discarded. On MapReduce they can be restored because it's all persistent on storage. But just in nearly all cases, it's cheaper to actually recalculate results than to persist everything just in case a task might fail, because most of the times tasks don't fail. Even if they do, it's usually negligible. So compared to the overall performance. So the concept of Spark actually works better in most of the cases, most of the use cases. Here there's an example for MapReduce. So these are static custom data types which are provided by the Hadoop framework. Then we have this mapping function, and the mapping function takes a key and a value and a context, and then it's inserted in the string tokenizer, and then getting tokens from the string tokenizer to actually apply the token to this word object, and then finally write the results into the context. And by writing it into the context, the framework gets notice of the result. So this would be the wrapper. This would be the reducer. You can see also here, this is also provided by the framework. And now our reduce gets an instance of this object which was created by the wrapper. So this word object here. And then it gets some iterable values, and then it's iterating over all the values, applying our reduction function, finally creating the result. This is also an object type which is provided by the framework. This is invitable. So we are storing the result in the invitable, which is then stored in actual storage. And finally, the context is written back the results, so now the framework knows that the reducer has finished this reduction step. And finally, this would be how our main program looks like. So we can see here that first we create a configuration, we create a job, which is basically done as a factory method for that. The factory method wants to have a configuration, but the configuration is going to be default configuration in the name. Then we set a jar file. So this is actually the one count class. This one, right, so on mapper. We also set a mapper class, which would be the tokenizer mapper, combiner class, and the reducer class. And now if you wonder what's the difference between a combiner and a reducer, well basically the combiner is doing the reduction step on a single node, and the reducer is doing the reduction step on across the nodes, so after shuffling, right? So because you always are able to reduce on a single node first, and then reduce the reduced result among the other nodes. So these can be two steps, right? So that's why we have also a combiner, but the combiner is optional. So always have to have a reducer, but the combiner can be identical to the reducer, but we can define a different way of combining. Then we set an output P class, which would be like this text class we have defined. And the output value class, in this case, is this convertible class. These are both classes provided by Hadoop. And now we need to add an input and output path for the job. In this case, these are just common arguments, so for input and output files. And finally, we can actually run all this stuff by running this wait for completion. And if, depending on the output, you can have an exit value of 0 or 1. So basically, this would be the main program for Hadoop, which would make this work. Some more steps are necessary to make it work, so we need to set environment variables, such as, of course, the Java framework. There also needs to be a Hadoop class path. We need to create a jar. We could have like example text files like this. So there could be two files, like file 01 and 02, with this content. So the first file would be like hello world, my world. So I mean, if you see, we have the world that has two occurrences in the single line. And in the other file, we have hello Hadoop reply to you. So we have single line, we have two occurrences of Hadoop, and across both lines, we have two occurrences of hello. And single line is single line. So now let's see what happens if we run this. So we can simply run it by pointing to the jar. And of course, this both pass to the input and output data. And then, if you look at the output, you will get what you finally expect. So we see, okay, number phi has one occurrence, the phi has one occurrence, Hadoop has two occurrences, hello has two occurrences, and world has two occurrences, right? And you see here the Hadoop has two, world has two, hello has two, right? So finally, these results are all combined. And this is the overall mapping, which is a result of reducing all individual p-value pairs. And group by key. And now if we look what actually happens in Hadoop, so the output of the first map would be hello one, world one, y1, world one. So this would actually be just protecting each word to the number 1. And then the second map would be the same. And now the first map, using the combiner. So now we have counted the word twice, but hello only once because the combiner so it's like on the individual node level, right? So only a single line has been processed. And also for the second map, we have counted Hadoop twice, but hello still once. Because here we have Hadoop twice in the same line, right? But hello is across both lines, so it's only counted once. So now we have two maps, which hello each counted once. And now the reducer actually, creates the shuffling and starts the framework actually, starts to move data around. So the reducer gets all the data, all the maps. In this case, there was two maps to be reduced. And then we actually have hello on twice, and also all values which are important points are in the different maps. So this would be like the final reduced result created out of all the individual maps. Yes, so this is the mapper result, this is the combiner result, and there is a node, and this is actually the reducer result. Okay, so yeah, that's how Hadoop basically works. Hadoop relies on the Hadoop distributed file system, but it's not only used by Hadoop, but also by Spark. How does this work? Yeah, basically, it's a distributed, scalable, and portable file system. It's implemented entirely in Java, and there are 5 services. They can be divided into master services and slave services. The master services are, there's a name node, a secondary name node, and a job tracker. And for the slave services, we have the data node and the task tracker. So what's the role of all these services? The name node only exists once. And basically all the metadata for all the stored data are indexed in the name node. And it does not directly communicate with the client. So it's there for use by HDFS itself, but not for use by the client. So it's a service available to the HDFS itself. Then the secondary name node is for certain management operations of the name node. So it's kind of directed to the secondary name node. The name node can offload some tasks to the secondary name node. And the job tracker is what actually accepts jobs from the MapReduce. So the job tracker gets jobs from the MapReduce. So actually, if you're calling an operation in MapReduce on the HDFS, then the job tracker gets these jobs. And then we have the data node, which actually stores the user data. This is temporarily reporting a heartbeat into a name node by using a heartbeat. And if this heartbeat is missing, then the name node will start replicating the data to another data node. So this is a kind of backup instance. So it's monitoring the data availability, and if it notices that data might get lost, then it will replicate the data. Of course, this only works if there are other nodes which still have the data, right? So that's why by default you have a redundancy in HDFS. And by default, this is actually a threefold redundancy here. So actually the data are always stored on 3 different nodes. So if one node fails, then you still have 2 nodes to get the data from. And then, because the data node is monitoring this, so if one of your 3 backup locations will have a problem, then they will immediately be replicated again with the threefold redundancy. So usually this works pretty well, because yeah, it's very, very unlikely that 3 instances will fail at the same time. So because they're distributed on 2 different nodes, right? So only, I mean, it might happen if you have like the 3 nodes on individual blade servers on the same rack, and then the rack is on fire or something. Maybe that could be a design decision, right? But usually it works quite well. Then they have the task tracker, which actually receives the tasks from the job tracker, and it also receives the mapper code from the job tracker. So the framework gives the mapper code to the job tracker, which then directs it to the task tracker. And then the task tracker is actually applying the mapper code to the data. And there is usually only one name node, but a cluster of data nodes. Yeah, you can mount the HDFS directly as a Linux file system. So basically, it's implementing the same API as regular Linux file systems are. And an interesting fact is that you can actually use Amazon S3 instead of HDFS, which is also some kind of distributed file system, right? So with MapReduce. So MapReduce actually has some kind of preparation for using with Amazon S3. So you can mount it use it yeah, with MapReduce framework, and it doesn't make a difference to MapReduce if you're using S3 or HDFS. Because HDFS, of course, must be usually it's something you have on premise. Basically, it's not a good idea to have your own HDFS on a remote cluster such as EMR, and then use it instead of S3, because then it will use the attached storages instances, which are usually more expensive than S3. So in this case, so if you want to do something on AWS, then it's a better idea to actually use S3 as the spike storage for data, since you can use it directly with MapReduce, so that's quite handy. Okay, so much for the HDFS. As I said, HDFS is something which can also be used with Spark, and it's still actively being used with Spark. Now let's discuss what Yarn does. Yeah, what is Yarn? Yarn is basically it's a resource manager, and the basic concept of Yarn is that you have a separation of the resource management and the job scheduling in different services. So we have a global resource manager, and we have an application-specific application manager, and we have a node-specific node manager. So basically we have instances, or kind of control instances on 3 different levels. You have one for the entire cluster, you have one for each application, and you have one for each node, right? Because application might, of course, work on several nodes, but not all. And yeah, what's an application in this understanding of Yarn? It's either a direct job, or it may be a directed acyclic graph of jobs like this. So yeah, as I have maybe said before, so a directed acyclic graph is basically just a graph which has no cycles, and yeah, it's directed. So it's directions, the arrows here, and there are no cycles, so it's important that it's cycle free, because otherwise you would never be able to terminate the job, right? Be stuck in a cycle. So that's why it needs to be acyclic, and so either a single job or a PAG of jobs. Yeah, this is yeah, it's an image from the Yarn documentation, but I'm not. Yeah, I think this is not so. If you look at this image, it's not entirely clear how it works, right? I mean, if you say you do understand it by just looking at this image, I would doubt that actually, because at least I wouldn't. That's why I want to explain this a little bit further. Yeah, basically you have the resource manager, as I said, the resource manager only exists once per cluster, and yeah, our clients only talk to the resource manager. So everything regarding the communication with the clients passes through the resource manager, but the resource manager does not so much more than talking to the clients. As you can see, we have individual node managers on each nodes of the cluster. And then we also have application masters. And you can see here, application masters are also placed on the slave nodes, but not on all of them, because, yeah, as I said, we may have fewer applications than the nodes, of course, which is usually the case. And the application masters can ask the resource manager for placing containers. So they have an application and they want to run it, so they need containers. And then the resource manager will actually give them a node manager which can then resolve them the containers. So the actual reservation of the containers done by the node manager, but the resource manager is coordinating. So the application master asks the resource manager, hey, I want to have a container, or I want to have several containers. It can be more than one container, and often is more than one container. And then the resource manager will tell the application master, oh, okay, now you can use this node manager and this node manager, then they will give you containers. And yeah, sometimes it can happen that the application master doesn't get all at once, right? I mean, that's something also happens to us sometimes, so we don't get everything we want, right? So because the resources are limited. So the resource manager is aware of the resources, the application master isn't, because the application master is not seeing everything, but only its local view of the node. So that's why the application master asks the resource manager, well, could you give me containers? And I would prefer to have so many containers, and then the resource manager will say, okay, but we only have so few containers, so you can have them. And it will actually give Node itself creating containers, but it will direct the application master to different node managers, and then the node managers will actually run the containers, acquire the resources for the container. And then the containers can be on the same node, or they can be on a different node. In this image, they're all on a different node, but it's not necessarily the case, right? So you can see here, so this container belongs to this application master, this container belongs to this application master. It could also be like this, yeah? So it's not prevented somehow. If it's a good idea to do that, it really depends on the application. But in general, the application master requests container or more containers from resource manager, and depending on the available resources, the resource manager will satisfy all the requirements or not, and tell the application master which node managers are there, which could reserve the container, and then the node managers who run the container on request of the application master. The containers can be on different nodes or on the same node as the application master. And now if you look closely, or maybe I think it's not really clear if you look at this image, but well, the application master itself is also running within the container. It's running within the separate container. And now you may ask, well, okay, now if the application master requests running containers, how does the application master itself starts to run, right? I mean, it's like chicken and egg problem. So that's why actually the resource manager itself runs the first container for the application master. So it's, the resource manager has a special role, so it can actually also resolve a container directly, but it only does so for running the application master. And then after the application master has been started, or further container requests which are subsequent to the application master are originating from the application master. Okay, so as I said, I think this is a little bit confusing because there are all these different types here of arrows with different semantics. And also the resource manager actually has two parts. So it consists of a scheduler and an applications manager. And they have different roles. But now let's maybe dive down a little bit deeper into this. First, the client. So the client submits the application to the MapReduce framework. So the application, as I said, it might be a single MapReduce job or this DAG of jobs. And then the client talks to the resource manager for requesting execution and also for monitoring the job status. So basically, if the client wants to be notified about the status of the job, it's always asking the resource manager, nothing else. And except for application master, so the application master can give us progress updates. So of course, only for the application we are looking at. So if we have different applications, we need to talk to different application masters, and which application masters are responsible is also an information which we get from the resource manager, because the resource manager is aware of all application masters. Then we have this resource manager, as I said, it's only once there for the entire cluster. And it consists of two components. We have a scheduler and we have an application manager. The scheduler is for the scheduling of, based on the allocated application and the available resources. It does nothing else, so it does no monitoring or tracking or whatever. That only does scheduling. And we have the application master. So the application master accepts the application from the client and it can restart the application master container if a task should fail. And it also acquires the first container. As I said, you have this kind of chicken egg problem. So there's this application manager, which actually starts the application master container the first time. Then you can also restart the application master container if it has the impression that the application master isn't doing what it should, right? So it oh, okay, no, I can't bring the application master container entirely, and just restart it. Now we have a new, fresh application master that might ultimately do what it's supposed to do. Yeah, so we have these two parts. Then we have node managers, and there's one for every single node. So the node manager, yeah, of course, as the name implies, it manages the individual node of the cluster, and it reports a heartbeat and a health status to the resource manager. So the resource manager is always monitoring this, so if a node heartbeat is missing, then it will know, okay, this node might have ceased operation. So let's do something about it. So then, of course, if the heartbeat is missing for a longer time, then the resource manager will not upload any more tasks to this node by other nodes. And move jobs from this node by other nodes. The node manager itself monitors the resource usage, and it also may terminate containers if the resource manager directs it to do so. So the resource manager may say, now please terminate your container for whatever reason, and then the node manager has to do this. But it starts the container process after the request of the application master. As I said, the application master asks the resource manager, now, hey, I want to run a container. And then the resource manager says, okay, there's a this application manager for this resource manager. And then the resource manager says, okay, please ask this node manager, I know here, this has some resources that could be available. And then the application master itself asks the node manager to start the application. Then the application master, yeah, as I said, it's one per application. As I said, application means a job or several jobs connected to it's responsible for the single application. It negotiates the resources with the resource manager. It also tracks the status and the progress of the application, and it sends a health report to the resource manager. And the request of the containers is a twofold process, as I said. So the first step is to ask the resource manager for an appropriate node manager. And now, if you have an appropriate node manager, the resource manager knows that this node has some resources available. Then it will send a so-called container launch context. So the container launch context is basically a collection of all the data required to launch the container. And then, this node manager will then use this container launch context to start the container and then start to monitor its resource usage. And as I said, so note that a single application master may request multiple containers, which are distributed across the cluster of several nodes. So it's not always like in this image that there's exactly one container or so, but there may be two containers, but there are just an example. So the containers may be anywhere on the cluster. They may be on the same node, the master, there may also be two containers running on the same node. So typically a node has running multiple containers on the single node also. But they don't have to run on the same node. So they could be distributed across the entire cluster and all reporting to the same application master. The application master may request multiple containers. It usually does request multiple containers, and it usually gets multiple containers unless the resource manager believes that it's running out of resources. In this case, the application master might not check all the containers at once. Okay, then, what's a container actually? As I said, there may be more than one container per node, and it usually is. So there are typically in production we have like 10 to 14 containers per node. In a experimental development environment, it may be more than maybe 2 to 10 or something. But in typical production environments, often you have 10 to 40 containers per node. Of course, it depends on the resources. So, a container is a collection of physical resources consisting of memory and CPU cores and storage space. And why are there so many containers? Basically, because you want to make use of all resources on a node, right? So often a single node will not actually exploit all the resources on this machine. So that's why we run several containers. And so we can make use of all resources, or at least most of them. That's why we run several containers per node. As I said, they're invoked via a container launch context. And what's in this container launch context? We have environment variables, security tokens, dependencies, and so on. So basically everything which we need to launch the container. As I said, the container itself is then launched by the node manager. And the node manager gets this CLC from the application master after the application master has gotten the node manager from the resource data. And a typical MapReduce consists actually of more than one container, usually. So at least you have one application master container. For any application, there's always an application master container. And then this application master container is run by the resource manager to manage the job. So as I said, it's the resource manager runs itself. Actually, the application manager is the resource manager. And then we have a number of Mapper containers. So one Mapper container is one per each input split. So depending on the number of input splits of your data, you have more than one Mapper container. And you also have reducer containers, and how many is this defined by the job configuration? The default is actually just one reducer container, but you may have more than one defined in the job configuration. So and if you look at this, so this can have at least 3 containers. So one for the Mapper, one for the reducer, and one for the application masters. Could of course be more, but often it's more. Actually in more recent versions of Yarn, we have so-called placement constraints, and they are divided into affinity and anti-affinity. What does affinity mean? That the containers are preferred to run on the same node as the application master. There may be situations where this is desired. And you may have also the opposite. You may have anti-affinity, which means that containers are preferred to run on a different node than the application master. But by default, actually, the application master is neither considering affinity nor anti-affinity by something different called data locality. So by default, the resources are requested for the data which are to be processed. So the idea is that, of course, it's not efficient if the resources are actually there where the data are, so then we don't need to move the data around, right? So this could be, for example, the according HDFS blocks. And since HDFS, as I said, is a distributed file system, so the application master tries to run the container at a place where most of the data are, which are supposed to be processed by the problem. So it's based on data locality, but there may be situations where this is not what you want. So in this case, you can have these placement constraints, and you could define it should run on the same container, same node as the application master, or preferably on a different node. Okay. So maybe a little bit confusing, but I guess I hope you get the idea. So this is a flow model. I found some accurate. First we start with the client. The client submits an application, and this is number 1. So the client submits its application to the resource manager, and the resource manager now allocates a container to start the application manager. Here. So now the resource manager starts allocates a container, then the application manager registers itself as a resource manager, then 4, and then the application manager notifies the node manager, the launch containers, and the application code is executed in the container. Client contacts the resource manager, application manager to monitor the application status, and once the processing is complete, the application manager administers the resource. So to sum this up, a single resource manager controls the entire cluster, and the client talks to the resource manager only, so nothing else basically. Just some status updates from the application master, and except for that, the client only talks to the resource manager. For every application, which equals to a get job, there is a separate application master, which controls this application. This usually runs on different nodes, but not always. You can configure this behavior. For every node, we have a separate node manager. The node manager controls all resources of the node. And the application manager requests containers from the resource manager. So the application master requests containers from the resource manager. And they may be located on the same or another node than this application master itself. The application master then directs the according node manager to run the container by issuing everything needed to run it as a container launch context. So the application master asks the resource manager, hey, I want to run a container. And the resource manager says, okay, use this node manager. And then the application master asks the node manager, hey, I want to run a container, here's my launch context. And then the node manager finally launches the container. The application manager regularly reports the status of its application to the resource manager. So the resource manager is always aware of all resource usage and the health status of all applications, not a single one. And the container placement depends on the resource availability of the nodes as well as the data locality. As said by default, it's actually the data locality, but we may adjust this behavior. And then the number of containers run per node depend on the available resources of that node. Okay, so that's Yarn. Now let's finally have a look at Hive. Yeah, what's Hive? So Hive has this logo with I guess Hive is the place where bees live in, right? So beehive. So there's this kind of elephant bee, whatever. Hive is a data warehouse system for querying distributed data with SQL. It's based on Hadoop and it supports S3 as well as HDFS. And it offers asset guarantees, but there are some conditions for that. So what's the concept of Apache Hive? SQL queries are translated into MapReduce functions, and then the compiled functions are transmitted to this MapReduce cluster, and also have a local execution, and the mapper scripts may be included. So this is an application example from the getting started of the Hive implementation. What you can see here, this would be our EDL, so our SQL for the equation. So we have a table which consists of, in this example, we have the int value for a user ID, an int value for a movie ID, and the int value for a rating, and also a string for a Unix timestamp. So basically, it's just a text file which has the source is a text file which has movie ratings, and then it's ID for the user who did the rating, ID for the movie which was rated, of course the rating itself, and finally time when this rating is done. And this could be like every line in the text file could be a separate writing by a separate user, maybe the same one, movie anyway. And now we can say, okay, this is our table format. And then we could have this would be like human data, then we load this data, then actually create a SQL table out of this data, and then run actually the SQL statement on this data. And it's, yeah, as you can see, it's quite simple like this. And now we could have like a Python script which actually does something with it. In this case, yeah, we want to actually investigate every line, like the Python script is doing here. So it's actually splitting the line and the data, and then it's converting the timestamp to the weekday, and then we can finally do something with the weekday, like in this case, taking out the weekday. And now in Hive, we can actually use this Python script like this, because the extraction of the weekday is now used. So we have here this table, then we have this Python file, and then here we are defining a transformation, which is using this Python file to actually give us this additional field of the weekday. So the extraction of the weekday is done by Python. And then we can select this in our SQL statement, like it would have the internal field of the SQL database, and also have to count on this. And you can even group it by the weekday. So you can group it by the field because it's extracted by the Python. And that's it. Yeah. So basically, you can see you can work with Hive as you could with SQL statements on files, and it's all done in parallel by using MapReduce framework. Okay. So far for this, then I would say, yeah, we just have like 15 minutes of a break, and then we go on.